Hello and welcome to today's session on AI and Selenium. Today we are going to be discussing some techniques and tools within the AI space that we can integrate into existing test automation frameworks. Before we get into our AI discussion, I'd like to talk briefly about my background and experience. I have over 13 years of industry experience as a software tester, engineer, developer, and architect. So for the origin story of my fascination with AI, a while back I was sifting through a large set of logs. I was trying to track down an exception that had caused a test failure that I'd ran into. And I spent hours and hours sifting through these logs. And as I sifted through, I started to see patterns in the logs that could be easily automated or easily translated into a test script, as a lot of what I was seeing could be described as user flows. However, I realized quickly that automating such a task would require a large amount of time and effort to gain coverage on these random edge cases that I'm finding in the logs. So to be honest, I sidelined the idea for a really long time. That was until I started reading about the advancements in AI and testing. Now, admittedly, most of the articles and presentations that I found on AI are all theoretical, right? So some of them are practical, but for the most part, they're theoretical. But honestly, that was enough of a spark to get me to go down the AI path, which brings me here today. Finally, I'd like to do a quick, interesting fact about myself before we get started. Number one, I love collecting video games from my childhood, specifically Sega Genesis and Xbox. And what's funny is now when I play them, I think how awful some of the AI is in those old games. Because when you think about it, the AI that they're trying to achieve in those games is similar to what we're trying to achieve during testing, right? We're trying to mimic human behavior. And it's just kind of fun to see how they handled that a long time ago and how we handle it today. And with that out of the way, let's get into an overview of today's presentation. In today's presentation, we are going to be looking at artificial intelligence to gain a general understanding of what AI is and how artificial intelligence can be used to enhance your existing automation frameworks. We will be talking about machine learning and deep learning techniques and how they can really be used to create models that can be consumed by existing frameworks, with a focus on convolutional neural network for vision and natural language processing for test generation. Then we will discuss an approach to integrating a convolutional neural network into an existing Selenium page object model framework, as well as a demo of using natural language processing to generate new tests from simple data. So let's start off with a simple question. What is AI? When you ask several people what AI means, AI is such a broad term that it's possible that you may get a number of different answers. One might answer in terms of the game AI example that I gave earlier, or another may bring up a new movie that they saw that included AIs taking over the world. But when I think of AI in terms of testing, I'm thinking of imitating human behavior, right? The user flows that we're going to be automating, their whole purpose is to imitate a human user. And what's interesting to me is that AI isn't new. It's been around since the 1950s. And the original principles still apply today among many of the new advancements, such as the deep learning branch of machine learning, on top of many other advancements in the AI field. And finally, is AI and testing hyped up? And the answer to that is a two-part, right? And kind of a cop-out, to be honest. And that's yes and no. I say yes because AI isn't to a spot currently that will allow any user with little to no knowledge or background in AI to simply tell the AI to test this site. It can get close with the use of some tools, some of which we will be talking about in a few slides, but for the most part still requires some human intervention of some form. And I say it's not hyped up because even though there is some human intervention, AI in the testing space has still come a long way. There are now pieces to that puzzle that used to take a full-on data scientist to put together that can now be performed by test engineers directly through the use of several different methods and techniques, some of which we will be going over in a few slides. So as we move through today's presentation, we're going to be talking about neural networks quite a bit. And as we do, it's important that you guys kind of understand what a neural network is. There's many kinds of AIs that utilize neural networks, and basically what a neural network is it's a set of algorithms that's loosely modeled after the human brain. Okay? It's designed to recognize patterns, specifically patterns in data. And as you can see, for our use case, we have lots of data in testing, right? So it's an easy transition to utilize a neural network to recognize those patterns in our test data. Now, there are 3 levels of AI. One being artificial intelligence, which is the ability that allows a computer to imitate human behavior. The next being machine learning, which is the ability to learn without explicitly being programmed, or, for example, it will use algorithms to parse data, learn from that data, and make decisions based on what is learned from that data. And the third level is deep learning. Deep learning extracts patterns from data using neural networks. For example, it will structure the algorithms in several layers to make what's called a neural network. That will then learn and make decisions by itself. So a form of machine learning that we can use in our existing test automation frameworks is called reinforcement learning. Reinforcement learning is based on the principle of having an agent and an environment. So the agent would be the code that you would be executing the actions with, and the environment is your application under test, such as your website or your mobile app. The agent's job is to find the best route to get to the goal. How it does this is by using what's called a queue function. The queue function will take the agent's state and actions available to the agent at its current state and calculate what's called a queue value. So for our example here, the game player is the agent, the game is the environment, and the castle is the goal. So as the game player moves across the environment, it will actually calculate its queue value based off of its state and actions available to it. Once it calculates that queue value, the game player will then choose the highest queue value to move. So for our example here, to get to the castle, if it calculated the highest queue value in its current position, the next move would be to move across the rainbow bridge, thus being closer to the goal. Now, reinforcement learning is great for environments with small amount of actions, but can be a lot more complex once you introduce several different actions. Additionally, reinforcement learning is used primarily for test coverage within testing, because you can use it to generate a number of paths throughout your application. Additionally, it's important to note that reinforcement learning can be used in combination with other techniques such as supervised learning to improve your overall outcome. A form of neural network we can use to integrate with our test automation frameworks is convolutional neural networks. Convolutional neural networks are primarily used for vision. How we can apply this to testing is that it gives our automation framework the ability to see the web page. It allows us to make element selections based on the label passed. This allows us to no longer worry about element properties such as ID or XPath, and instead focus on creating new tests. And the feature extractor can be attached to any type of output you want, classification, detection, whatever. And the concept of how a convolutional neural network works is fairly simple. You have your input, which is your data set, and then next in the step is the convolutional layer, followed by the pooling layer and the fully connected layer, where we apply our labels. And finally, we have our output, which would be the model that we would consume by our test automation framework. Next, we'll do a deeper dive into the convolutional neural network's workflow so you can get a better understanding of how that process works. So here we have a basic convolutional neural network workflow. We have our input, our convolutional layer, our pooling layer, our fully connected layer, and our output layer. So what does each do? So our input layer is our data set. So in a convolutional neural network, that would be a directory that has lots and lots of images of different categories. So for example, if we were doing a convolutional neural network on cats and dogs, we would have lots and lots of images of cats and lots of images of dogs. The second layer is the convolutional layer. So the convolutional layer can really be looked at as a filter, as this layer is where a filter will be applied across every image and a feature map will be generated from that image. The pooling layer is where we downsample the feature maps created and add invariance. The fully connected layer is where we will apply the labels to the image. And this is important because when we go to ask the model for classification, we will pass this label to the model. Finally, we have our output layer. This is where our model will be generated and is the same model that we can consume inside of our test automation framework. Now that we have a general understanding of the process flow, I want to now discuss what is happening within a few of these layers. So here's a simple workflow of how to load a data set. You first load the data set of images, so our directory of our example of cats and dogs. Then we need to set the categories for each data set. So pictures from a website may have login, cart, LinkedIn, etc. for their categories. Then we need to prepare the data. So we need to resize the image to the size that will be applied to all images, as the convolutional neural network will expect a specific size. Then we need to set the color scale. Is it grayscale, 2D, or is it RGB, 3D, etc. Then we need to create test and training data. The test data will be a subset of images from the data set to validate your images. Note, test data should not be included in your training data. Then we need to shuffle the data so that the model does not overfit. That means that it is overtrained on a specific piece of data. Now let's jump in to see what's happening in the convolutional layer. As you can see here, we have a beautiful grayscaled image of an apple. To the right of that image, we have a square with numbers in it. The green square represents our image that we are passing in, so the grayscaled image of the apple. The yellow square represents the filter that will be applied to the image. The square on the right represents the feature map that will be generated as the filter is applied to the image. So what's happening here is that we have our picture of our grayscaled apple, and we will apply our filter across that image. And as it moves across the image, it will generate what's called a feature map. A technical way of saying this is the filter slides across the input image, element-wise multiply, and adds the outputs. But again, what it's doing is basically taking the image, sliding a filter across that image, and generating what's called a feature map. And it will repeat this process for every image within the dataset. And after the feature map of the image is created, a label will then be applied to the image. So for our example of the apple, because the apple was within the apple category, the label apple will be applied to the image. So for a more testing related example, say we have a website that has a login button. To set up our data set for the login button to be fed through the convolutional neural network, we would set the login within a subdirectory of the dataset called login. That subdirectory would be considered the category for the login button. After a feature map of the login button had been created, a label would be applied to that login button called login. Now let's give a bare bones example of generating a model from code. The example here is written in Python and is using TensorFlow and Keras. In the code, you will see that the model will be ran through sequentially. We have two different convolutional layers here. This is important because not every convolutional neural network will be the same. Many of them will have a different number of layers, depending on what type of outcome you are looking for. It's also important to note that tweaking is a huge part of the process here, as it may take several attempts at generating a model to get your desired outcome. If you decide to move forward with generating your own model, there are a few things that you may run into. One of them being overfitting. It can be very frustrating to have trained a model for hours only to find out that the model has become too accustomed to the data set that it's been generated off of. Overfitting is when the model has trained too long. Another example that you may run into often is called underfitting. This is opposite of overfitting. This is when your model hasn't trained long enough. Both overfitting and underfitting are fairly common occurrences, and both can result in poor performance of your model. The key here is to get a sweet spot when the model has the right amount of training. How to achieve this? You can do several things, right? But the two things that I recommend are early stopping, which stops the training if generalization errors begin to occur, and model checkpointing, which can capture the best val accuracy, for example. So now that we have dove pretty deep into what a neural network is and how we can generate our own convolutional neural network model to be utilized within a test automation framework, let's take a moment and focus in on some existing automation frameworks. There are a number of test automation frameworks out there in the wild, with some of the highlights being data-driven frameworks, keyword-driven frameworks, and PaLM frameworks. For the purpose of this presentation, we will utilize the Selenium page object model framework, as they are incredibly popular within the test automation community and have had the ability to mature over time within several different development life cycles. They are easy to read and understand and have proven scalability options, as well as encourages reusable code. That's not to say if your desired framework is not listed that it's not supported. The approach I will show can be integrated into a number of different types of frameworks, from Selenium to Cypress. So let's start off by looking at the architecture of a Selenium page object model framework, which I'm sure a number of those in the audience are familiar with. The first layer in our page object model is our test scripts. This is where we write our test steps and call our page objects for elements on the screen. The second layer is our page objects. This is where we will define our web element properties and write our test methods that utilize those web elements. And the third layer is our web page, or the application we will execute our code against. So now let's focus in on our page object class. At the top of the page, we have our web elements. This is where we define our web element properties. So our IDs, our XPath, our selectors, etc. Below that, we have our page class. This is where we store our test methods, which include our actions. And in this scenario, our actions actually call our defined web elements at the top of the page. In a perfect world, because our actions are based on our defined web elements, we would only have one sole location to change if any of those IDs had changed. Some maintenance risk areas for this setup would be that the properties to the web elements can change frequently. This can happen for a number of reasons. For example, a portion of the web page may not be under your team's control, or the IDs themselves could be dynamic by design. The next high-risk areas are test methods and actions. So my example earlier was in a perfect world. If we have our defined web elements at the top, there should be only one sole location to change if any of those element properties are changed. However, in the real world, it's fairly common that you may have to write some custom code and set the element properties within the test method. For example, selecting an element from a list. This can cause an engineer to need to come back to the same section of code to refactor from time to time. So how do we reduce this maintenance risk? The first thing we can do is we can start to look at including a convolutional neural network model inside of our Selenium test automation suite. This approach would allow for elements to be selected based on the label passed to the test script, which no longer requires us to define an element within the page object class. This reduces the overall maintenance of the page object class. As we no longer have to define elements, test methods with custom code will no longer break because they require specific properties, and overall saves the testers time in defining the web element properties. Before we integrate our convolutional neural network into our Selenium page object model, we want to identify an AI strategy. So we want to identify what are AI candidates and what are our non-AI candidates. What do we want to automate using AI and what do we want to keep manual? In this case, we want the AI to define our web elements for us via the convolutional neural network. The second piece is what we are trying to achieve. And what we want to achieve in this scenario is lower our maintenance get faster test authoring, and allow for easier element selection via the convolutional neural network. So from our AI strategy that we laid out, we know that we want to use AI to select our web elements within our application. Knowing that, we can now identify the steps we need to integrate the convolutional neural network into our page object model. The first thing that we will need to do is collect a list of web element images from the page. Second, we need to capture the identification for each web element within that list. So as we collect the list of images associated to the web elements, we will also collect the web element themselves and associate it to the image. We can then send the list of the elements to the convolutional neural network. The convolutional neural network will then predict, based on the label passed, that the label matches the web element. Once the prediction is returned, we can now perform an action on the element requested. Now let's review our Selenium plus convolutional neural network architecture. So the first layer, we still have our test scripts, where we still write our test steps and call the page object class. However, this time, in layer 2, we now have a convolutional neural network within our page objects. So in our test scripts, we would pass our label to the page object class that now contains the convolutional neural network. And then we have our web page layer, which is our application under test, where we execute our tests. So you can see here the main difference between the previous architecture is that we now only have one page object class that contains the convolutional neural network. So let's deep dive a little bit into the convolutional neural network page object model class and what that entails. At the top, you will notice that we are no longer defining our web element properties. We now have a classification method, and this classification method will be used to call out or load the AI model generated. Below that, we still have our class, and within that class, we now have a generic method. And that generic method's job is to simply take the label that we are passing to it and pass it along to the classification method via an action. So you can see here where the maintenance risk that we had before around defining web elements and our custom code within our test methods is significantly reduced, as they are no longer required to make an element selection. Now let's walk through the Selenium and convolutional neural network test architecture using some code examples. We have a test script here called test homepage that contains a test example. At the top, we have our label. This is the label that we will pass to the convolutional neural network for classification. With our test example, we are setting up our driver and creating an instance of the page class that contains the convolutional neural network classification method. You'll notice that this is similar to how a normal Selenium test is set up. We can then use the generic method from within the page class and pass our driver and label to it. In this example, we are passing sign-in as our label, as we want the AI to select the sign-in button. Then, once the element prediction is returned, we will perform an action on the element being returned. In this example, the action will be a click. Then we do some normal exception handling. Now let's jump into what's happening in the generic method within the page class. Within the generic method, we set our driver to find elements by a query parameter that is being set above. We then create a dictionary for our element images to be stored in called element images. Then we create a list to store all of the elements returned from the convolutional neural network called possible elements. Remember, the convolutional neural network may return more than one, depending on the model's accuracy. Now we loop through the list of elements from the page that we collected, and as we do, we take a screenshot of each element and pass it to the classification method, along with the label passed from the test script. The classification method will then attempt to classify the image against its known categories. If a match is found, it will return the possible element for action. Now that you've seen the process flow and code, I'd like to cover some caveats of using a convolutional neural network model within Selenium. The first one is that test runs may take longer, and this is due simply because of the element collection that is required to pass along elements to the convolutional neural network. During that element collection, each element needs a screenshot taken of it, and this process can take a very long time. On top of that, compatibility across browsers can be affected, as the screenshot capability within Selenium may differ across browsers. The second caveat is model accuracy. If the model that you are using has a low accuracy, then your test performance will be very low. What I mean by that is that with low accuracy means that the chances of the model being able to accurately classify the image that you are passing with the label will be significantly reduced. The third caveat that I want to cover is that this method specifically does not completely eliminate defining web elements, as there may be some cases that require you to still define web elements. These cases may include needing to create a test case that requires a web element defined that isn't accurately being classified by the model, or when wanting to quickly set up an ad hoc test. And finally, the fourth caveat that I want to cover is the complexity of understanding how a convolutional neural network model works will require some technical knowledge and know-how to be able to completely understand what tweaks need to be made in order for the model to be more accurate. Now I would like to switch gears and talk about natural language processing for test generation. Specifically, I'd like to talk about OpenAI's GPT-3 text generator and how we can integrate it into our automation testing frameworks. If you are not familiar with what OpenAI's new GPT-3 text generation tool is, GPT-3 comes from the company called OpenAI. OpenAI was founded back in 2015 by Elon Musk and Sam Altman to advance the state of artificial intelligence. It's a huge leap forward in artificial intelligence and is able to generate text, create poetry, translations, answer questions, and generate code. It can even create mobile applications in milliseconds. It's absolutely amazing. With this new technology tool, you can now utilize GPT-3 to generate test code from a simple data source. So how does GPT-3 work? GPT-3 works off of a basic example prompt output model. For example, the user inputs a few example prompts and includes what they expect GPT-3 to respond with from those example prompts. Then, for the prompt, the user inputs simple text similar to the context of the example prompts given and submits it to GPT-3. After the prompt is submitted, GPT-3 will then generate an output in the same context as the example outputs given above. So how do we approach integrating OpenAI's GPT-3 into our test automation? The first thing we need to do is set up our use case. Our use case in this example would be to convert simple text into test code, generate the test scripts from the output, and run those test scripts. Now, converting simple text to test code can mean a lot of things. We could either write manually simple text into a prompt and send it to GPT-3, or we can tie it to a data source such as analytics and generate test code from that. Now that we have our use case, we can now look at how we would apply GPT-3 to our test generation. So for the first step, we need a subset of examples to send to GPT-3. So for our use, we could use a subset of test data as our prompt. And for our expected response, we can supply what the code would look like for that test data. The second layer, the prompt, is simply a list of test data that we want to send to GPT-3. For the third layer, output, is simply GPT-3's response to our prompt of test data. What we are expecting here is the test code that we supplied, similar to the example. And for the fourth layer, we simply need to write a method that will generate a test from the output of GPT-3. So let's take a look at an example of what the GPT-3 plus test automation process flow would look like. The first thing you need to do is you need to provide the API with 4 to 6 examples. The reason for 4 to 6 examples is that's what I've found to be the best result. For the example, we need to send a sample text of what we want to test. So for our sample here, we're going to send create a new Chrome driver and go to google.com, then select the search button. Then, after we give the sample text, we need to tell GPT-3 what we expect. For our use case, we expect a code output. Now that we have supplied GPT-3 with an example, we can now send our actual prompt. Our actual prompt will consist of simple text or data that follows the context of the examples given. So for our example here, our prompt will say, create a new definition called AI Gen script with a new Chrome driver and go to amazon.com and select the cart button. Once we submit this prompt to GPT-3, GPT-3 will return an output with the converted test script. The only piece left that we need to do is then run the Selenium tests that were automatically generated. Now let's take a quick look at a test generation demo using OpenAI's GPT-3 and our test automation framework. In this demo, we will convert simple text to Selenium test code. We will then automatically generate test scripts based off the output returned from GPT-3. So as you can see at the top, we have set up an instance of GPT. We then add an example to our GPT-3 instance. And finally, we set up a list of prompts to send to GPT-3. Once GPT-3 returns the output, we will then feed that output to a generate file method, which will then generate test scripts based off each output. The test files will then be generated into the gen test folder. As you can see, each generated test follows the proper Selenium format. In today's presentation, we included several different techniques in integrating AI into your existing test automation framework, from reinforcement learning to convolutional neural networks to natural language processing using GPT-3. The following is a list of open source tools that are available to you that can help kickstart your model generation. Using the techniques that we showed today, you should be able to use the library shown here to be able to help you get AI integrated into your test automation framework. The open source tools that I suggest is TensorFlow, which is an open source software library for data flow, and Keras, an open source natural network library written in Python. There's also the PyTorch/fast.ai combination, which I highly suggest for beginners. PyTorch is an open source machine learning library based on the Torch library, and fast.ai is a nonprofit research group focused on deep learning and artificial intelligence. I'd like to end this presentation with a few recommendations that I have on getting started with generating AI models. If you're a beginner, building your own convolutional neural network using many of the widely available tutorials is often the best way to gain a better understanding of how neural networks work. Remember, if your accuracy is coming out low, remember you can tweak your model a little and try again. For example, more or less epochs, add or remove layers, etc. The second recommendation is to get comfortable with TensorFlow or PyTorch usage. Review the documentation and excellent tutorial videos the community has put together. And finally, think simple. When dealing with neural networks in general, it's important not to make things complex for complex sake. What I mean by that is that some of the tutorials or the documentation you may read surrounding AI may come across initially as overly complicated. So I encourage you to not let your frustration fog your mind when dealing with building your own neural network. And if you feel confused, remember to go back and reference your use case, as sometimes you may find you are headed down a path that isn't necessary for your specific use case. Or if you're having problems with accuracy, please consider transfer learning. Transfer learning is how to take a model that already knows how to do something well and make it so you can do your thing really well. By doing this, you can sometimes train models in 1/100th of a time when compared to regular training.